Hi everyone, welcome to the course on microsensors and nanosensors. We are discussing the 9th module where we are talking about occupation and motion sensors, and this is the second lecture in this module. In the previous class, we have discussed about ultrasonic occupancy sensors, and we also have talked about microwave occupancy sensors. Okay. So, what we are going to do today is we will take forward the microwave occupancy and motion sensors, and we will also see some other kind of sensors in today's lecture. Okay. So, let us see microwave motion sensors. If you remember, ultrasonic sensor or ultrasonic occupancy sensor was simply based on a transmitter and a receiver, and we have discussed that a diaphragm can generate a piezoelectric diaphragm can generate ultrasonic wave, and it can also act as a receiver because piezoelectricity is a reversible phenomena. Okay. But since microwave cannot be generated by these diaphragm kind of structure, we have to come up with a microwave motion sensors altogether as a different entity. Although we will see that the principle will remain more or less similar, which is the Doppler's effect, but the generation of microwave transmission, okay, and receiving is quite a different challenge as compared to a ultrasonic occupancy sensor. Okay. So, a microwave motion sensor typically consists of a oscillator, which is mostly the gun oscillator because they can generate RF signals. Okay. And they have a antenna and a mixer. They have other components also like amplifier and frequency meters, but mostly these three components are very crucial in a microwave motion sensor: a gun oscillator, antenna, and a mixer. Mixer is mostly a mixer diode, which is mostly a non-linear device. We will see that. Okay. So, gun oscillator is as the name suggests, is based on gun diode. If you do not know gun diode, I will suggest that have a look on the principle of gun diode. I will just try to cover it in very brief. Okay. So, gun diode, this gun oscillator is used to generate microwave RF signal without needing a conventional resonance circuit, okay, which will make it bulky, and gun oscillator can generate microwave RF signals, and as the name suggests, I have mentioned that it is based on gun effect, which was discovered by J.B. Gunn in 63. Okay. So, in the gun oscillator, a diode, which is basically a gun diode, is mounted in a small precision cavity that oscillate at a microwave frequency when power is applied. Okay. So, this gun effect is not shown by all the materials, but it is specific to certain semiconductors like some compound semiconductor like gallium arsenide or indium phosphide. So, when an electric field exceed a threshold voltage, a negative differential resistance, which is NDR, appears, as you can see in the IV curve. So, this is the negative resistance regime. Okay. So, when the electric field exceeds a threshold value, a negative differential resistance appeared, as you can see in the IV data of this gun diode. Because of this, the electron transfer to the higher energy valley with a lower mobility, which causes the current drop. Okay. So, the oscillator, this kind of gun diode is helpful in developing a gun oscillator, and the oscillator generates electromagnetic wave, say for example at a frequency of f0. Okay. So, a part of this frequency, a part of this wave passes through an iris into a waveguide, and then you focus it on the antenna. Okay. You can see that this is the oscillator, gun oscillator. This is generating the RF signal or the microwave signal. Okay. And this frequency f0 is passed through a waveguide. So, please note that this was not the requirement in the case of ultrasonic wave. Okay. Because there will be more attenuation there. Okay. So, a part of this passes through a iris into a waveguide, and then you focus it on antenna. Okay. This radiation towards the target object. Okay, this antenna radiates it to the person who is moving or towards the object which is in motion. Okay, mostly this microwave sensors are more useful in motion detection. Okay, so this antenna transmit this frequency f naught, and this f naught is related to the wavelength lambda naught by simple expression of f naught is equal to c naught by lambda naught, where the c naught is the speed of light in air. Please note that in the ultrasonic occupancy sensors, we have not used this kind of frequency, because that is the frequency very near to the sound wave. Okay, and now we are talking about a frequency or a speed which is nearly of the light. Okay, the microwave travel with the speed of light because it's a electromagnetic wave. Okay, so f naught is equal to c naught by lambda naught. This gives a simple expression for the frequency. We'll use this equation later on. Okay, so now when the target moves towards or away from the antenna, the frequency of the reflected wave will shift. Okay, if the target is moving away at say a velocity v, the reflected frequency will decrease and it will increase for the target which is approaching the antenna. Okay, and again this is based on the Doppler's effect that we have discussed in the previous class. Okay, so although the effect was initially discovered for the sound, this Doppler effect can also be applied to the electromagnetic radiation. Okay, however, for the sound wave, the propagation speed can vary depending on the movement of the sound source. Okay, whereas for electromagnetic wave, which always travel at the speed of light, this is constant and independent of the light source movement. Okay, or the sound source movement. Okay, the frequency of the reflected electromagnetic wave can be estimated using Einstein's special theory of relativity, which suggests that this Fr is equal to f naught into root 1 minus v by c naught square by 1 plus v by c naught. Okay, in this equation, this is the velocity of the movement and c naught is the velocity of the light. Okay, and this Fr is the frequency of the reflected electromagnetic wave. Okay, practically for relatively slow moving object, when I say slow, please note that I am taking the reference of movement of this electromagnetic wave, which is traveling at 3 into 10 power 8 meter per second speed. Okay, so anything object which is moving on earth will have much smaller speed as compared to this. So practically for relatively slow moving object, this term v by c naught square will be very small. Okay, so if say v is at, it's a train and it is moving at, or it's a aeroplane, it is moving at very high speed. Okay, say it is moving at say 300 meter per second. Okay, or even say 3000 meter per second, which is too much. Okay, then also this term will be very small. Okay, particularly the square term. Okay, so for relatively slow moving object, this term v by c naught is very small as compared to this value 1. Okay, and therefore this v by c naught square can be neglected as compared to this 1. Okay, so now if I neglect this, this term will become Fr equal to f naught by 1 plus v by c naught, right. So this simplification makes the equation for the reflected wave frequency identical to that we uses for acoustic or ultrasonic waves. Okay, so this Fr is equal to f naught into 1 by 1 plus v by c naught. Okay, if I simplify it, it will be f naught 1 by c naught plus v into c naught, or c naught by c naught plus v into f naught, right. So as followed by this equation, the Doppler effect causes the reflected wave to have a different frequency, which is denoted by this Fr. Okay, now this goes to the mixer diode or mixing diode. Okay, the mixing diode, as I have mentioned earlier, is a nonlinear device. Okay. So, it combines the reference or the radiated signal and the reflected frequency. Okay. Now, when it combine them together, it generate a signal that include multiple harmonic of radiated and reflected frequencies. Okay. So, say the electric current through the diode mostly is represented using the polynomial as shown over here. Okay. The polynomial for electric current for this kind of diode is given as I equal to I naught plus AK into U1 cos 2 pi f naught t plus U2 cos 2 pi FRT power k, where I naught is the DC component in this current, okay, and AK is the harmonic coefficient that depend on the diode's operating point, and this U1 and U2 are the amplitude of the reference and the received signal, and this F naught and Fr are the frequency of the reference and the received signal or the reflected signal, right. So, this is the equation for the current for the mixing diode. Okay. I is equal to I naught and summation of this k equal to 1 to n, then AK, which is the harmonic coefficient which depend on the diode's operating point, and this term power k. All right. Now, the current through the diode contains an infinite number of harmonics if you solve this equation, okay, among which there is a harmonic of a differential frequency which is of our interest. Okay. So, this delta f is given as A2, this is coming from this AK. Okay. Delta f is equal to A2 into U1 into U2 cos 2 pi F naught minus Fr into T. Okay. And this frequency is known as Doppler's frequency in the case of microwave motion sensor. Okay. The Doppler's frequency in the mixer can be found from delta f as F naught minus Fr. So, say this is my second equation. Okay. The Doppler's frequency in the mixer can be found as delta f, which is F naught minus Fr, and Fr we have already calculated, and if I put that this Fr value, if you remember, we have calculated from this equation. Okay. Fr is equal to F naught into 1 by 1 plus V by C naught. Okay. If I put this value in this equation, okay, I will have this delta f is equal to F naught into 1 plus C naught by V. Now, since this value is much higher as compared to 1, you remember that we have taken this V by C naught square as a negligible amount as compared to 1. Now, this term is just reverse, C naught by V. This is very high and this is very small. Okay. So, this term is much higher as compared to 1. Okay. And therefore, if I substitute this like delta f, I can write as F naught into 1 by C naught by V. Okay. Or delta f is equal to V by C naught into F naught, or delta f in the terms of lambda can be written as delta f is equal to V by lambda naught. Okay. Where the lambda naught is the wavelength of the initial or the reference signal. Okay. Now, this equation holds true only for the movements of the object in the normal direction. Okay. Now, when the target moves at some angle with respect to the detector, the Doppler's frequency will also contain one angle term which is in terms of this cos theta, and this delta f will equal to V by lambda naught into cos theta. Okay. Now, my signal has reached to mixer. Something will come out of this mixer that we have already seen. Okay. The frequency we have already seen. Okay. Now, this mixer output signal typically range from some in terms of voltage, it will be like microvolt to millivolt for a good amount of movement. Okay. Now, this voltages are very small, therefore, we need a preamplification. So we have amplifier for further signal processing. Okay. Now, since this Doppler frequency falls within this audio range, the amplifier design remain relatively simpler. Okay. However, usually it will need another frequency filter, which is notch filter. Okay. So what notch filter will do is it will reject a power line frequency, and the main harmonic from the rectifier, full wave rectifier, is in the range of say 60 to 120 hertz. Okay, in the filter. Okay, that's how a microwave motion sensor detect with the simpler amplification but complicated gun oscillator and antenna. Particularly the coupling of this is very important. Okay, and the post processing after the mixer is much simpler as compared to the other component, and that's why we have given more stress on this three part: mixer, oscillator, and the antenna. Okay. So this is a very basic of a microwave motion sensor, how it works. Okay. Then we also have capacitive motion sensors. We'll see some example of a practical capacitive motion sensor, how or at least if not motion, capacitive occupancy sensor. Okay, fine. So let's see an example of a human body or movement of a human body. Okay, so the human body forms a capacitive coupling with its ambient because it is a conductive material with a high dielectric constant. Okay. So the capacitance is significantly influenced by a number of factors, including the body size, type of clothing that I am wearing, materials, nearby objects, weather, and multiple things which is affecting the capacitance. Okay. This capacitance from the body, as I have mentioned, that it depends on number of factors. Okay, but usually it vary in the range of certain picofarad to a few nanofarad. Okay, and the movement of a person causes change in the coupling capacitance. Okay, which allow differentiation between a static object and a moving object. Okay, that's why I told that although we are discussing occupancy sensor, but we can also design capacitive motion sensor on the very similar principle. Okay. So as I have mentioned that the capacitance from the body depends on number of factors, including the body shape and size, the type of clothing I am having. Say if I am wearing some textile which also have some conducting portion, it will have different dielectric properties. Okay, if I am wearing very thick woolen clothes, it will also increase the dielectric properties. Okay, then the nearby objects also can make capacitance with us. Okay, we'll see with one example. So what is nearby to us, those things affect this. Okay, and whatever is affecting the capacitance is nearly in the range of few picofarad to few nanofarad, depending on all these factors. Okay, and as I have mentioned that movement will cause changes in the coupling capacitance, which allow to segregate moving object from the static or a still person. Okay, so all objects exhibit a certain level of capacitive coupling relative to each other. Okay, so if you are sitting in the classroom, you are also making some kind of capacitance with the say on the desk on which you are sitting, or say if there are some metal plates around you, you are also making some kind of, or even with earth you are making some capacitance. Okay, so if a human enters the vicinity of an object with a already established coupling capacitance, the presence of the intruding body introduces a new capacitance value between them. Okay, so earlier there was a established capacitance, and if something is disturbing it, okay, there is a new capacitance established and the total capacitance changes. Based on the same principle, there have been different capacitive occupancy sensors reported. Okay, let us understand this with one example. Okay, say The figure shows the capacitance between a test plate, this is a test plate, okay, and the earth, okay. So this plate is making a capacitance with the earth, and the, say I am calling this capacitance as C1, okay. Now when a person enters the vicinity of the plate, okay, he is coming near to the plate, it generates one capacitance with this plate which is Ca, okay, I am calling it Ca. However, it is also generating another capacitance with earth itself, okay. So this Cb is established between this body and the earth, okay. So earlier this plate was making one capacitance with earth which is C1, and now when a person or an intruder comes into the vicinity of the plate, it is making two additional capacitances, Ca which is between plate and the body, and other is Cb which is between body and the earth, okay. Now the resulting capacitance C between the plate and the earth becomes larger by the incremental capacitance delta C, and let us see this delta C, okay. So this Ca and Cb, if you see, are in series, okay. So this delta C will be equal to the series connection of Ca and Cb, okay, which is equal to Ca, the overall capacitance will be Ca Cb by Ca plus Cb, right. Initially the capacitance was C1. Because of this person, the capacitance has increased by delta C, and now the total capacitance will be C1 plus delta C, or C1 plus Ca into Cb by Ca plus Cb, okay. We can use the same principle to have more kind of capacitive sensor. Say consider a car is there or a automobile is there, and we have to, we have parked it somewhere, and we want to know that if the driver's seat is occupied by someone or not, okay. If someone is stealing my car, or my car is still available at the parking, okay. So usually this car seats will have capacitive occupancy sensors integrated, okay, for the security purposes, okay. So please see this example, okay. A sensing probe is integrated into the car seat. Say this is a car seat, and a sensing probe is integrated into the car seat, okay. Now this integration can be done by various ways, say by a metallic plate which is placed beneath the table, beneath this chair. There can be a metal net placed on it, or the cover can itself be a conductive fabric, okay. So a sensing probe is installed in this car seat, okay. This probe is installed in the car seat, okay. So this constitutes the one plate of a capacitor, okay. I am talking about parallel plate capacitor. So this constitutes a single plate of the capacitor. The second plate of the capacitor Cp, this Cp is created either by the car's body, which is also a metallic, or by an additional plate which is located beneath the floor mat of the car, okay. Now the reference capacitor Cx is a simple capacitor, and it is adjustable, okay. It is mostly adjustable, okay. This should be located in a close proximity to the seat probe, okay. The probe plate and the reference capacitor are connected to the input of a charge detector through this resistance R1 and R2, okay. The conductors should be preferably be twisted, and there has been various research in this twisting also, because this twist decides the capacitances, okay. So this conductors is usually twisted to minimize the introduction of unwanted signals, okay. Now there is one oscillator which control a differential charge detector. This oscillator is controlling the charge detector, okay. when the seat is unoccupied, the reference capacitor is tuned to be roughly equal to Cp. Since this is a variable capacitance, I have made it when there is no one is sitting on this chair, the Cx is tuned to value of Cp. Okay. Please note that in this case, the resistors and capacitor as any RC circuit define the time constant of this network. Okay. And RC circuit will have a time constant, say T1, and the resistor voltage are input to a differential amplifier, okay, which produces an output voltage Vc that is approximately equal to 0. Okay. In this condition, when there is no occupancy, this Vc is approximately equal to 0. Now, small spikes at the output is the result of some unavoidable imbalances. So, this Vc may have some values, therefore, we have another step, to avoid any false alarm. Okay. So, when a person sits on this car seat, his body introduces an additional capacitance in parallel to the Cp. Okay. As a result, the time constant of this circuit, this R1 Cp network increases from tau 1 to tau 2. Okay. The increased spike amplitude at the output of the differential amplifier indicates this, and it comes as a voltage Vc. The comparator compares this Vc value, this is fed to this comparator, okay, and you already have a threshold value or a reference value. Okay. The comparator compares this Vc value with the predetermined threshold value, so which is set based on calculation of the body weight or taking into consideration the minimum weight expected. Okay. Now, when the spike surpasses the threshold, okay, the comparator triggers an indication signal to the logic circuit, which then generate the signal V indicating car occupancy. Okay. So, you had this oscillator which generates these charges, okay, and the small signals were ignored, and it only triggers when it was occupied by using the comparator. Okay. Now, it should be noted that a capacitive detector is an active sensor, because you are always using this oscillator to generate the test signal. Okay. This kind of sensor is just one example. Based on this, you can design a number of different capacitive occupancy sensors, but please note that this kind of devices that we have discussed is mostly for occupancy purposes. Okay. And mostly it doesn't have to do much with the motion detection, but we also have seen another example of capacitive sensor where we have used it for motion detection. Okay. Or even the occupancy detection. I am talking about the previous example where the person was making capacitance with the earth and the plate. All right. So, however, this capacitive occupancy and motion sensors doesn't come with all the advantages only. There are certain disadvantages associated with this capacitive motion sensors. Okay. Particularly if you see in this scenario where you are making the car seat itself as a one of the plate, and you have used another capacitance which is which can be tuned or which is changing. These things make this system very difficult to be calibrated. Okay. So, this kind of system have complex calibrations, and they are also very susceptible to noise, which can be decreased by various means. Okay. Particularly, you have seen that to avoid false alarms, we have used comparators. Okay. So it minimizes the chance of false alarm, but then since you are using, there can be various parasitic capacitances along with the original capacitance that we expect. This is mostly susceptible to noise, okay, and the range of this capacitive sensor is not that high, okay. And then there is another disadvantage that in both the cases, if you see, the person has to be in close vicinity to the plate, or he has to sit on the chair, okay, on the car seat, okay. So this capacitive motion sensors or occupancy sensors work only well when the person is in vicinity, and mostly it is a contact kind of sensor, or near contact kind of sensor, okay. But for security applications, we have also seen non-contact sensors like microwave sensors and ultrasonic sensors. They are useful when you want actually a non-contact based sensor. So all these sensors have their advantages and disadvantages, okay. So what we will do is we will also talk about other kind of sensors, particularly the triboelectric and others that we have not covered yet in our coming lectures, okay. So thank you.